Hi everyone, and welcome back to our final week of the semester in data analysis. The topic for this week's lecture is called Who Cares About Statistics? And I'll say it's my absolute favorite topic in this class, and probably the reason that I request to teach it over and over again. Before we get into the lecture, though, I just want to go through a couple of end of the semester reminders and announcements. This is the final week. Not finals week, don't confuse it with finals week. This is the final week of the class, so once you're done with anything you want to do this week, you are totally done with the class. And as you should also be aware, everything this week is optional, so last week was the last required problem set. So this week we have a makeup problem set, and as I'll discuss in a second, we also have an extra credit opportunity. All right, so the makeup problem set. If you complete this problem set by Sunday of this week, you can use your score to make up for any lower score earlier in the semester. So if you missed a problem set, this can fill in for that. If you just got a low score on a problem set, this is an opportunity to increase the score. So it's up to you if you want to do the problem set. You will also notice that the syllabus, if you're following that, I'm sure all of you are following it closely, but if you're following that, it originally had this due on Thursday, since that's Wednesday or Thursday, since that's actually officially the end of the semester, but I just put the due date on Sunday as usual to give everybody a little bit more time. All right, then we also have something that is not in the syllabus, and that's an extra credit opportunity. And to be perfectly honest, part of the reason that I have this is that I love this lecture and I want to incentivize you guys to actually watch it. So if you watch the lecture and do this extra credit opportunity, you can add up to 3 points to your overall score. So that's more than 1% of the grade, and it can bump you up as need be. And if you decide to do the extra credit opportunity, that will also be due on Sunday at midnight. But again, both of these are optional. Calculating your grade. So a question that you might be having now is, should you do the makeup problem set, and should you do the extra credit opportunity? And if you want to answer that question, I recommend taking a look at the grading scale that I have here. And so this is how grades are assigned in the class. This is ripped right out of that syllabus. And as you can see, there are points in the class that correspond to a percent score. So you can go on Blackboard, check what your total points are, and then see where they fall in that scale of points. If you have 224 points already, congratulations, you already have an A. If you have less than that, that's where the makeup problem set or extra credit opportunity can come in. So you can just see where you fall in this distribution here and then decide from there which of the optional assignments you want to do. All right, and with that, I'm going to get to the content for today's lecture. And today's lecture is all about the use and abuse of statistics out there in the world, and especially the kind of things that you might encounter when you're just reading the news or going through life and seeing numbers about things. And so as you've probably noticed, just by being alive, statistics are everywhere. They're often cited in the news, they're cited by politicians, universities throw them at you all the time. Really, whatever you're doing, you can't escape statistics. So knowing a little bit about how they're used and how they're sometimes misused can be really, really helpful in just navigating the world and all the numbers that it has in it. So we're going to focus today on 3 specific things that are somewhat related to each other. One is that random variation being treated like it's meaningful can lead to misleading or misused statistics. Another is that correlation being confused for causation can be misleading and misused. And then another thing, finally, is that findings that are statistically significant are sometimes treated as being meaningful or substantively significant when they're not. And this is also something to look out for. So I'm going to talk a little bit about each of these 3 things, and then that will conclude our semester. All right, first topic. Things vary, and sometimes it doesn't mean anything. I actually want to start by posing you with a question, and I want you to think about this while I put it up here. The 2013 murder rate in Newark was almost double the 2003 murder rate in Newark. These are true facts based on statistics you can find online. However, the murder rate in Newark has stayed about the same for the last 20 years. So just think about that for a minute. The 2003 murder rate in Newark was going the other way, about half of what the 2013 murder rate was in Newark. So that looks like a huge jump, right? From 2003 to 2013, we have so many more murders in Newark. However, the murder rate in Newark has stayed about the same for the last 20 years. Also a true fact. So how is this possible? The answer to this question has to do with probability. And as we've learned in this class, when you have a probabilistic event, so any event where random chance plays a role, which could be the roll of a dice, it could be the sample statistic you get when you take a sample from a population, anything where probability plays a role means that when you repeat that event over and over again, you're going to get different numbers, different statistics, different outcomes just by chance. And so we saw this when we talked about probability with the idea that if you repeat some sort of event, just by chance, you're going to get different outcomes. We saw this in sampling, where if you repeat a whole bunch of samples, you're going to get different sample means or different sample proportions or whatever, just by chance as you repeat those samples. And this is also true of something like a murder rate, where the number of murders in a year is probabilistic in the sense that even if you have kind of a steady number of murders that's likely to occur, some years you're going to happen to have more murders and some years you're going to happen to have fewer murders. And it's going to vary just by chance because there's just so many different things that can go into how many people happen to get murdered in a year that even if the overall rate is pretty steady and there's no real increase or decrease in how likely murders are to occur, some years you're just going to have more murders and some years you're just going to have less murders. So what this means is that a murder rate is going to be higher in some years and lower than in others, even if it stays about the same on average. And this idea is encompassed in something called regression to the mean, which essentially says that you might get a high number or you might get a low number, but things are generally going to get back to a single average, assuming that there's no chance in whatever that base probability is. So again, regression to the mean is dealing with the idea that if you're repeating measurements of the same outcome, so you're repeating the same measurement over and over and over again, just by chance, sometimes it's going to be high, sometimes it's going to be low, but it's always going to come back to that same sort of average value, and it's going to wiggle around it. What this means is that if you compare a year that happens to be very high to a year that happens to be very low, it might seem like there's a really dramatic change. But what's really happening is this. And actually drew this picture just for this slide. You get a murder rate that looks like this, where as the years go on, so as you move out to the right on that x-axis there, your murder rate is, again, sort of wiggling around this same amount. And as you can see, it's not really going up or down much. It's more or less a wiggly straight line. But some years you just happen to have a lot of murders, and some years you just happen to have relatively fewer murders. But it always comes back to that mean value. So that's why we're saying it's regressing to the mean. And so if you think about the murder rate in 2002 versus the murder rate in 2013, what you're actually getting is a picture that looks like this, where 2002 was a dip that happened just by chance, and 2013 was a peak that happened just by chance. And if you were to compare only those two numbers, you'd see a really dramatic increase from 2002 to 2013. But in reality, murder rates never skyrocketed. Instead, they've just been wiggling around this sort of average value for roughly the last 20 years. So the takeaway here and the moral of the story is never rely on just two data points to tell you about a trend and whether something is going up or down or how it's changing. Because if you only have two data points, you can never be sure whether you have a real trend or whether you have something that looks like this, where you just have one that happens to be low and one that happens to be high just by chance. So you'll see this oftentimes used as well by people who want to make a point about a trend about something. And so this is something that you really have to be on the lookout for. And I want to show you a billboard that I drove by for a long time when I lived in Albany. And every time it made me mad because it's such a good example of how two data points doesn't really tell you anything. And so this is a billboard that's put up by the Correctional Officers Union in New York State. And they want you to be really, really concerned about violence against correctional officers in prisons. And as a quick aside, obviously violence against correctional officers in prisons is problematic. We want people who work in prisons to be safe at their jobs. But this is a very misleading use of statistics. And the reason is that we only have one bit of information here, which is that assaults on staff went up by 55.1%. Okay, seems like a big number, right? 55, that's large. But what we don't know is what the overall trend looks like. And so it's possible that what we're seeing is a wiggly line, and last year it was down here and this year it's up here, and that's an increase of 55.1%, but it's just going to keep wiggling after that. And so only showing this single increase that's based on 1 year and then some other year that's 55.1% more, and they don't even tell you the time frame here, which is worse actually. But still, it's really based on 2 data points, which is some baseline and then one that's 55.1% higher. And so with this little information, you don't know anything about what's going on with prison violence. You don't know if it's doing this and we happen to just have a low year and a high year, and you can't look at this and make any sort of meaningful conclusion about trends in prison violence. So again, this is something to look out for. If you see just 2 data points or something like, an increase of whatever percent, which is using 1 data point and then the next year to make a statement about how much it increased from that time, be cautious in interpreting those statistics as meaningful, because you might just be seeing that sort of wiggly line variation, and it's just going to regress to the mean the next time it's measured. All right, so that was one thing to look out for. Another thing is correlation versus causation. And this is one that seems to be more widely known by people. It pops up in memes and stuff sometimes. But correlation versus causation. We're going to talk through what it means and then give some examples of that as well. And correlation versus causation is all about something called spuriousness. And what spuriousness refers to is when you have a situation like this. You have some variable z that causes some variable x. Your variable z also causes some other variable y. X itself does not cause y. So we have 3 variables, one of them causes the other 2, and the other 2 do not cause each other. What happens is that your variables x and y will appear to be correlated until you account for that variable z. And so here's an example. There's a correlation between eating ice cream and being attacked by sharks. So the more ice cream that people eat, the more shark attacks there are. And so if you think about this, we have a variable x, which is going to be our cause, eating ice cream, and some other variable y, being attacked by sharks, which will be our effect. So we have a correlation between these 2 variables. Eating ice cream is correlated with shark attacks. Does this mean that eating ice cream causes people to be attacked by sharks? Well, let's think about it. Maybe if you eat ice cream and you're swimming, you're more likely to get a stitch in your side, and you're gonna not be able to swim as fast away from the shark that comes at you. Maybe. Or it's possible that we have a spurious relationship between these 2 variables. And rather, there tends to be more ice cream eaten when temperatures are higher, and it's warm and people are at the beach and whatnot. And there's also more shark attacks when temperatures are higher and it's warm and people are at the beach. So higher temperature causes more ice cream to be eaten, and it also causes more people to be attacked by sharks. So there's higher ice cream scales and higher shark attacks, and those things are correlated with each other, but neither one is causing the other. So instead you have this confounding variable, or this variable z, that is causing this relationship to appear causal when it's not. So it makes it look like ice cream sales cause shark attacks, when really both of them are caused by higher temperature. And I have a couple more examples of these. So there's a correlation between the number of churches and the number of bars in a city. Does this mean that more churches cause more bars to happen, or that more bars cause more churches? Is it that people go to church and then they're suddenly inspired to drink? Is it that people who go to bars, must reevaluate their lives and find religion, so they start more churches? Probably not. Instead, we have a spurious relationship, where the more people you have in a city, the more bars you have, and the more churches you tend to have. And it's not that one causes the other, it's just that there's some third variable there that's causing both of them to occur. So you get this spurious relationship where it looks like they're causal, but really they're not. Another one, there is a correlation between the number of speeding tickets that somebody gets and the number of accidents that they get into in a car. Does this mean that the more speeding tickets that somebody gets causes them to get into more accidents? So police officers give out some tickets and, you get a ticket, you're upset, and then you're gonna drive less carefully and get into an accident? Maybe, but it's much more likely that the number of speeding tickets and the number of accidents that happen are both caused by the same thing, which is the number of miles that somebody drives. So the more time you spend in a car, the more likely it is you're gonna get a speeding ticket. And the more time you spend in a car, the more likely it is that you're gonna get into an accident. So those two things aren't related to each other causally. One doesn't cause the other to happen. Instead, you have a spurious relationship where both of them are caused by something else. And then finally, I've put this one under my head while I'm recording it so I can't see it, even though I'm going to move it after I post the PowerPoint. But we have, I'm going to make a really good guess at what's under my head. We have a correlation between height and some sort of academic ability. So the taller a child is, the better they are at reading or math. Does it mean that being taller makes children better at reading or math, and that, we should be putting all our tall children into reading and math programs and just, say, oh, those short children, they're never going to make it in school, like, let's not even bother? Probably not. Instead, we have another spurious relationship where the older a child is, the taller they are, and the older a child is, the better they are at reading or math. So it's probably that last one, where age is something that's causing both height to occur and causing academic ability to occur. So these are all examples of spurious relationships, where you have a common cause between two variables that makes it look like they're related to each other, makes it look like they're correlated, when in reality, they're not really. So this is why you should never confuse correlation for causation, because you can have variables that are correlated with each other when neither one is actually causing the other one to happen. And here's an example from real life. So this is something that I pulled from the internet, but this was an actual message sent out by a university trying to convince students to join their study abroad program. And the message was that studying abroad is going to help you graduate. It's going to help you get accepted into grad school. It's going to help you get a job too, because look at this. Study abroad students are more likely to graduate on time. 90% of study abroad alumni report acceptance into their first or second choice grad school. 97% of study abroad students found employment within 12 months compared to 49% of students who didn't study abroad. Wow, right? So you have all this information that makes it sound like studying abroad is causing students to do better. Because as you can see clearly, studying abroad is related to academic and job success. But what we have here is a pretty classic example of correlation versus causation. And so studying abroad is correlated with good outcomes in terms of academics and job success. So there is a relationship where people who study abroad are more likely to have good academic success and good career outcomes. But the issue is that there's so many different things that could be common causes of these variables that we can't say that studying abroad actually causes students to do better. So one example of a possible common cause is that students who study abroad tend to be more academically motivated in the first place because they have to apply to these programs, they have to make things happen on their end to get in, so they're also going to be more motivated when it comes to doing well in other areas of school, or they're going to be more motivated when it comes to the job market. Another explanation has to do with money. Students who study abroad may have more resources than students who don't study abroad. And having more resources is helpful in doing better academically and also helpful in getting a job later. So this ad here makes it really sound like studying abroad causes students to do better. And obviously, you should sign up for a study abroad program right away if you want to do well in school and get a job afterwards. But it's really misleading because there's so many different reasons that these two things could be related to each other that have nothing to do with one causing the other. So the moral of this story is always think critically about causation when you see statements about how two things are related to each other. So when you see statements about correlation. And I really recommend anytime you see something like this, just take a moment and think, is there any reason that these two things would be related to each other that doesn't have anything to do with whether one causes the other one? All right, my final topic for today's lecture, significant findings. And so in the last unit of this class, we've talked a lot about statistically significant findings. And we know that a statistically significant finding occurs when our hypothesis test tells us that there is some significant effect. In other words, if you're comparing means, there's a difference between the means, and it's significant in our sample, so we have evidence that there's really a difference in means in the population as well. If we're looking at correlations, if you have a significant correlation based on a sample, you're saying that based on this sample, we have reason to believe that there is truly a correlation in the population as well. So statistical significance, again, is all about, whether your sample is giving you evidence of some statistical effect existing in the population that you're trying to make an inference to. So this is a pretty technical definition, right? So it's based completely on whether your sample gives you some sort of evidence of an effect in the population. And as we also learned, statistical significance is based on a threshold that's set by the researcher, the alpha level. So if you have an alpha level that's very, very strict, like 0.001, it's harder to get significant findings because you're saying that sample results have to be really, really unlikely to, tell you about the effect in the population. If you have an alpha level that's more lenient, like 0.05, you're going to have significant results much more because you're saying that the sample results don't have to be as unlikely to provide evidence against our null hypothesis about what's happening in the population. Where this comes into play in research results in the real world is that the typical standard in social science research is that research findings count if p is less than 0.05. And so a lot of the times what researchers do is they run all their models and then they just sort of go through and they look at all their p-values, and if it's less than 0.05, they say, oh good, this one counts. Oh good, this one here counts. These are our findings because p is less than 0.05. And what this means is that in research, the most common alpha level is 0.05. So basically, if your sample results would occur less than 5% of the time, given some null hypothesis about the population, if you're in that less than 5% of the time zone, we're saying that we have evidence against our null hypothesis, we have evidence in favor of our alternative hypothesis, and therefore our research findings about the null and alternative hypotheses, they count, right? They are statistically significant. The problem with this, well, there are two problems, but the first problem with this is that you get something called false positives or type 1 errors. And a type 1 error is when the null hypothesis is actually true, so there is no effect in a population, but you find an effect in the sample. So you reject the null hypothesis, even though the null hypothesis is true. So it's a type 1 error if you reject the null hypothesis, even though the null hypothesis is true. So basically, your sample finds evidence of some effect, so a difference in means or a correlation, whatever effect you're looking at, even though no effect like that exists in the population. So really, the population means are the same, but in your sample, you just happen to have a big enough difference in means that you're able to reject the null hypothesis. There's really no correlation between two variables in the population, but in your sample, you have a big enough correlation that you're able to reject that null hypothesis and conclude that there really is a correlation in the population. So it's called a type 1 error because it's a false positive. There's also a type 2 error, which is the opposite of that. So it's failing to find evidence of an effect when there is an effect, but we're not really going to talk about that otherwise in this class. But I want to talk about these false positives a little bit more in the context of research findings. If you have an alpha level of 0.05, this means that you actually have a baseline 5% false positive rate. So with an alpha level of 0.05, just by chance, your sample findings are going to allow you to reject the null hypothesis, even when the null hypothesis is true, 5% of the time, because we're rejecting it based on that 5% of least likely samples. So when you have an alpha level of 0.05, anytime you do a statistical test, there's pretty much a 5% chance that you're going to accidentally reject the null hypothesis when really the null hypothesis is true. And 5% might not sound like much, but it's 1 in 20. And just think of all the hundreds and thousands of studies that are done. 1 in 20 studies, based on this 0.05 alpha level, are going to be false positives, or give these type 1 errors that show an effect based on the sample when really there is no effect in the population. And just as a note, that's a little bit of a simplification because many studies have multiple hypothesis tests in them, so it really gives you even more chances for type 1 errors. But just as a baseline, you have this 5% false positive rate when you're using an alpha level of 0.05. And this happens just by chance. So no matter how good a study is, no matter how much researchers are really trying to get good quality results, just by chance, the way that hypothesis tests are set up, 5% of the time, you're going to get a false positive. And a way around this, of course, is to use a more strict test, so to use a lower alpha level. But with this sort of general norm in the social sciences, especially, and in some other fields, to use 0.05, it means that most of the time, researchers are working with this sort of 5% false positive rate. And what you can see in this picture here that's ripped from the XKCD comics is that p-values are often also sort of interpreted by researchers depending on how good they make the findings sound. And if it's very, very low, that's good evidence in favor of rejecting the null hypothesis. Highly significant, that's great. The closer you get to that 0.05 threshold, everybody's aware that it's weaker evidence, but hey, it's still significant. And then when you get beyond that, oftentimes people will just keep talking about those effects as though they're statistically significant because you're just kind of close. And so that's where you see that highly suggestive, significant at the 0.10 level. But there you're getting into really sketchy territory because if you have a p-value of 0.1, you're saying that there's basically a 1 in 10 chance that whatever effect you found is just totally, completely by random chance. And it's not actually reflecting anything in the population. So I'm going to stop getting into the weeds of p-values here, but when you see research findings and you see p-values being cited, it is sort of important to be aware of how they're being interpreted. And to be aware that the bigger your alpha level, the bigger a p-value, the more likely it is that whatever finding you found is a false positive. There's also another problem in significant findings in research, which is something called p-hacking. And p-hacking refers to any practices by researchers that are used to try to get a p-value below 0.05 so that you can say a finding is significant. And oftentimes it's not really done maliciously. It's more that researchers have a really good idea, they collect all this data, they run their models, and then they find, oh, there's no significant findings here. We have no evidence in favor of whatever hypothesis it is we like. But that can't be right because it's such a good idea. So let's just crunch the numbers in a couple of different ways and see if any significant findings pop up. But a problem with this is that the more times you do a hypothesis test, the more chances you have to get that false positive. And so if you run enough tests, there's a good chance you're going to get a false positive. And the more tests you run, the more likely it is that you're going to get a false positive. And so you end up with these false positive rates that are actually way higher than 5%. Because you have people running the same tests over and over again or running them in very similar ways over and over again. And an example of this that I like is from a study that wanted to set out to show how easy it is to get a statistically significant finding that's completely meaningless. And so this is an excerpt from their study here. And in the study, they asked 20 college students to listen to When I'm 64 by the Beatles or Kalimba, which I think is like elevator music. And then they gave their birth date and their father's age, and they used father's age as a control variable, which we didn't talk about here, so don't pay too much attention to that. And what they found was this effect. When students listened to When I'm 64, they became a 1.5 years younger compared to when they listened to Kalimba. P equals 0.04. So we have a statistically significant effect here. It is statistically significant that students who listened to When I'm 64 became younger than students who listened to Kalimba. And so if you think about statistical significance and hypothesis testing, this would be like evidence saying that based on this sample, we can say that anybody who listens to When I'm 64 is going to become younger than anybody who listens to Kalimba. But obviously that doesn't make any sense whatsoever. And what happened here is that the researchers did a lot of what's called p-hacking. And so this is sort of the revised version of what they actually did. And so they had them listen to way more songs than or I guess 3 songs rather than just the 2. They actually started with 34 students, but they cut students out. They measured a whole bunch of different variables, and then ran a whole bunch of different hypothesis tests using those different variables, and then controlling for different things. And I haven't actually read the fine print in a while on this, and I just realized one of the variables is which of 4 Canadian quarterbacks they believe won an award. So they're just measuring like totally random stuff and running a whole bunch of hypothesis tests in order to get a false positive. And it turns out that when you do that, one of the false positives that appears is listening to When I'm 64 rather than Kalimba while controlling for father's age causes people to, it causes people to become younger. But again, that's a totally not true effect, and it's just statistically significant by chance, because through all this p-hacking, they were able to give themselves, a type 1 error, so a false positive, just by chance. And just to clarify here, because you may need to know this for the problem set if you do it, a type 1 error just refers to getting a false positive by chance. So finding a statistically significant finding in a sample when really there is none in the population. Or in other words, rejecting the null hypothesis when the null hypothesis really is true. P-hacking, on the other hand, refers to using techniques like measuring a whole bunch of variables and combining them in different ways and running a bunch of different hypothesis tests in order to try to get yourself a type 1 error. All right, so the moral of this story is don't assume that every statistically significant finding is also meaningful. And I would say especially if it's something that's important. So, with many false positives, it's not the end of the world. But if you're going to actually sort of think about how you see the world or change your behavior or vote or whatever the case might be based on a single significance test, try to look into it and see how the significant findings were found. Because while hypothesis testing is really, really useful in that it can give you good evidence about whether something is true in the population, it's not totally infallible either. So it's good to be sort of a critical consumer of statistics like this and to be aware that statistical significance doesn't always mean real significance. And rather, statistical significance is a technical term based on hypothesis testing, which is just a really useful tool for learning about what's true in the population, but not an infallible one. And if you do the extra credit, you'll have a chance to look at a sort of fun real-world example in which people were able to fool millions into believing a false effect here. Before I get into that, though, I'll say one more moral of the story is that moral of this entire lecture here is not supposed to be that you should ignore all statistics, but rather that it's just good to think critically about them and to think about things that might be misleading about them or not. And my hope is that this class has given you some tools that will help you do that as you sort of go out into the world and just, you're already in the world, but as you encounter statistics, as you go on with your lives and your careers. All right, so with that, I'll talk about the extra credit. So a couple years back, you may have seen headlines that said that eating chocolate is going to help you lose weight. And they appeared in some pretty big outlets like Huffington Post and Self magazine, and a whole bunch of others as well. And they were all based on a single study that said eating chocolate is a good way to lose weight. As it turns out, this study was a complete hoax that was done by a researcher who wanted to show how easy it is to get a false research finding and to get it out into the news. And so it was written up as a sort of a blog post article type thing called "I Fooled Millions into Thinking Chocolate Helps Weight Loss." So if you do this extra credit opportunity, I want you to read this blog post article thing. I don't know what you call it on IO9, but read this It's not super long. It's not academically written at all. It's just meant to be read by people. And it explains how they were able to fool people using statistics into thinking that chocolate helps weight loss. And after you do that, I want you to answer the following 2 questions. One is, how did the authors use hypothesis testing to prove that chocolate helps weight loss? So tell me what they did. It's all explained in the article, but tell me how they were able to use, these hypothesis testing techniques we've been learning to prove falsely that chocolate helps weight loss. And then tell me what was wrong with that conclusion. So once you know what they did, it should be pretty obvious what was wrong with it. But tell me what was wrong with that conclusion and why it was actually a false finding. And then you can turn in the answer on Blackboard. So with each of these, this will be on Blackboard as well, I'm only looking for, like 1 to 2 to 3 sentences at most. I just want to see that you read the article and absorbed the information. And if you decide to do it, just turn it in on Blackboard by the end of the week this week. So this is all that I have for you guys for the whole semester. And so I will end this lecture by saying, y'all were great in this very strange semester online that we had, and I hope you have a good holiday and rest of your lives. All right, the end.